Introduction: The self-balancing bike is an application of the concept called as inverted pendulum. Inverted pendulum is an unstable, non-linear system where a weight is kept in upright position even in the presence of external forces, just like trying to keep a stick upright in a hand. It is a fusion of mechanical and electrical concepts used as benchmark for testing modern control strategies. Multi-body Simscape. Multi-body Simscape requirements define the physical environments and constraints necessary for simulation. The inverted pendulum is modeled by importing parts designed in Fusion 360 and connecting them with hinge joints after proper alignment of frames. External disturbances are applied at joint 1 using a pulse generator combined with a randomizer simulating unpredictable pushes. Tilt angle theta from joint 1 is measured and compared to the reference upright position, that is theta is equal to 0 degrees. A PID controller computes the corrective torque, driving the reaction wheel at joint 2 to stabilize the pendulum. These are some graphs of the Simscape simulation. First graph shows disturbance every second with varying extent of those disturbances. Those disturbances cause excitations and spikes in theta every time on every second as seen in the second graph. When there is a disturbance, the omega, that is the speed of inertial wheel, it changes to compensate for disturbance and hence produce stability, which can be seen by theta attaining 0. Program overview. MATLAB program block handles all the MATLAB part like sensor data processing and logic. The motorcycle block handles the input of sensors and output to motors. Motorcycle block. This block handles output to motor of inertial wheel for balance, rear wheel for movement, and servo for steering. This output data is received from program block. IMU sensor, encoder, and battery voltage is taken as input and sent to the program block for processing. MATLAB program block. Balance is controlled by a PD loop, where Kp for theta is the proportional element and Kd for theta dot is the derivative element. A feed-forward wheel compensation term, which is a product of Kpw and inertial wheel speed, anticipates destabilizing effects of wheel motion, improving transient response. In criteria chart, enable and safety logic uses user input, IMU sensor calibration, theta, and battery voltage to decide whether the motors are allowed to drive. When enabled and safety checks pass, the controller command for inertial wheel and rear motor command are sent to the actuators for stabilization and forward motion through the filter. Sensor processing of MATLAB program block. Sensor processing block filters and processes raw IMU data and outputs theta, theta dot, inertial wheel speed, IMU calibration status, along with battery voltage. Criteria chart of MATLAB program block. User input, IMU sensor calibration, battery voltage, and theta are used to decide if balancing should be executed or not. Since inertial wheel-based inverted pendulums have a saturation point, recovery of bike is impossible beyond certain tilt angle. Controller value determination. First, decide Kp and Kd values, the proportional and derivative elements. The bike should at least oscillate near the balance point. Fine-tune using the Kpw gain value for longer stabilization duration. Bias on theta in sensor processing block may need adjustments depending on ground levelness and weight imbalances of the bike. Note: avoid random value entries. Applications: robotic stability, self-balancing vehicles just as this one, ship stability, fighter jets, earthquake-resistant buildings.